Let me start this video by saying don't try anything that I'm about to show you at home. The voltages and currents that I'm working with are definitely lethal. Of course, I've designed the transient generators that I'm going to use for some of these tests, so I'm very comfortable conducting these tests. So let's go ahead and get started. Hello again and welcome. This is just going to be a short follow-on video for this Fluke T6 that I'm looking at. You can see I've soldered a set of batteries into this. I've been running a few tests on it. So obviously one of the things I did was partially reverse engineer the meter. What we ended up with was a 1K ohm resistor, and that's in series with a PTC that has a DC resistance about 1.3K ohms. And then that's in series with a gas discharge tube. And then I believe that the input impedance on this, when it's in the volt mode, was somewhere around 1.2 mega ohms. So let's just ignore that for right now. And then this goes down to the negative lead. So this is our red wire here, and this is our black probe down here. So then this black wire, of course through the back cover here, connects up inside of this contact here, and then this goes through this network. Now we don't really know what this network is. It's just kind of an unknown. And then this goes down to our finger button. Now, there's a gentleman named Modemhead who took some measurements of this network, and he measured somewhere around 2.2 nanofarads. Now, of course, what I was saying in my video is obviously this is going to be frequency dependent, but it's 60 hertz. If you look at the impedance of this capacitor, I think it worked out to 1.2 mega ohms. What I was saying in my previous video is I test these very high frequency transients, not at 60 hertz, and because of that, what I'm worried about is that the impedance of this capacitor would actually be quite a bit lower. Now, there was another gentleman who had actually taken this cover apart. Essentially what you saw was a network of 5 components in series. Now we could assume that there's probably some capacitor in here and some resistor as a minimum. Again, there's 5 components, so it's probably some combination of multiple capacitors and resistors. And we know the total capacitance of that works out to be roughly 2.2 nanofarads. The problem is in the video it looks like those parts could all be roughly 1206 packages. It's a little difficult for me to tell, and again, I didn't take mine apart. So a resistor in the 1206 size is typically rated for about 200 volts. Capacitors in this range are typically going to be around 50 volts. It's just a ballpark. So you end up with 5 of these things together. So, you know, maybe a kV or so. Let's just say that this whole network can handle. Typically what I've seen on meters is they'll use MOVs here, you know, rather than a gas discharge tube. And those MOVs are typically in series. There's normally 2 of them. And there could be multiple legs feeding down to this one here. That's pretty common. So this will be our return path, and this will be our input. And you'll end up having this same 1.3K and 1K combination. And then these MOVs will be typically rated for, you know, 800 volts or so. So the total breakdown of this is going to be about 1600 volts. So we put that in series with this 1000 volt breakdown of this network, and the entire meter would break down at, you know, somewhere around 3 kV. If you watched that previous video, I thought it was kind of funny because people were talking about watching the whole thing, but there was a part right buried in the middle of the video, and I had a piece of rubber hose, and it was attached to a potentiometer that was controlling that 5000 volt power supply. And I physically took my hand and I connected it essentially to the output of the power supply. So I've got this power supply here, and this is rated up to 5000 volts. The negative side of this went to a plate, and then my hand basically was attached to this plate, and this was attached to the meter, and then I had the red lead attached to the power supply. So far in all the videos what we've seen is people are basically applying 120 volts AC to the meter in this same arrangement and they show that they're not getting zapped by this thing. So what I did is I slowly increased this thing up to the point where this network broke down. So if you watch my hand very closely in that video, you can see as soon as this breaks down, my hand jerks. And then what I did is I caused it to break down a second time, and you can see me trying to pull my hand away from that plate. And you can see it's a little difficult. And the whole reason using the rubber hose, of course I got my hand out here, hand number 2, with this piece of rubber hose, and that's attached to a potentiometer. The whole reason that I have this rubber hose here, and I'm basically insulated, is I don't want this current to somehow pass through my 2 hands. So I just want this nice controlled loop here where I'm not going to end up getting hurt by this power supply. So if you watch that video, what you're going to find out is this entire meter, which includes this network, breaks down the first time at about 3,000 volts. And then what I ended up doing was I went back, I caused the meter to break down a second time, and I tried to pull my hand off. And that second time, the meter broke down, I think, at roughly 3.4 kV. So it's somewhere in this range, somewhere below 4,000 volts. So I'm curious now, regardless of what this network is made up of, if the human is holding on to this pad and they are grounded and the meter is in any mode, again, this network is always in play. So the black lead is inserted into the back of the meter. So this network's in play. And so that would be a normal way to run the meter, but for some reason they take that red lead and they attach that to the hotline. Normally it's not a problem. But now what happens, again, this is a cat rated meter. What happens if this voltage reaches something greater than this voltage where the meter breaks down at? So let's say it reaches some peak voltage here of, let's say, 8 kV. So I know now at that level, this gas discharge tube is actually fired. And I also know that I've broke down these 2 capacitors. Again, the whole reason running the DC current through this instead of the AC is I'm not dealing with the impedance of the capacitor in this network anymore. I'm looking at the breakdown voltage of it. So once that breaks over, and now I have a low impedance path, and now what I have is this thing riding on top of the main AC line. So if you look at this for real, it's just going to be a very short pulse. Again, for the surge testing, this transient has a full width half-height of 50 microseconds. So that's a very short pulse compared to the 60 hertz. But now I have all this energy sitting in this waveform that can pass through this. Now, I don't know what it would take to injure a human, but it would be very interesting to run a test like this. You know, put the transient right through the entire meter and just see what would happen here. And unfortunately, I don't know what you would use for a model for a human being other than, you know, a human being, and just see, you know, does the human even feel that? I can guarantee you with the DC voltage, you know, I definitely felt it. If you watch that video, you can actually see my hand contract. Now normally, like I say, if the meter's attached to, you know, 120, 240 volts AC, DC, whatever, this isn't going to break down. And the currents are going to be so low, I doubt you'd even feel it. If you go back and you look at the IEC standards, there is a section in there where they talk about current limiting devices. And that section will talk about the maximum currents that are allowed. And I have to believe, again, that under normal conditions, this network is going to work just fine for that. What I don't know is if that section of the standard considers you hitting this thing with a surge or some other high voltage pulse and having that network break down. Again, I'm not a safety expert. I'm not affiliated with any company that's designing products like this. I don't really know how those standards would be interpreted. We do know that the meter has a CSA mark, so it somehow got certified. Yeah, so I'm half tempted to try to set something up. Like I said, I just don't know what we would use. What do you use down here for a model for the human? How do you characterize it? And I don't know. Again, I do like the meter. You know, I think it's a very novel idea. I could actually have a use for a meter like this in my normal job. I would never use a meter like this to tell me that a circuit is live or not before I go in and work on it. But, you know, as far as taking some basic measurements, I definitely could see using a meter like this. And I definitely think it would be a lot more safe, you know, using this non-contact feature than going in there and probing it with a conventional meter. So one of the things I'm thinking is basically I could take the meter and I could attach it between the button and the probe tip. Again, it doesn't matter what function we have this thing in because the circuitry is always engaged. And basically what I could do is apply a high voltage transient using this generator here. And again, the way that this works is if the meter breaks down, which we know it will because this generator will put out close to 6,000 volts, and we could just see what happens with this meter. And if this meter gets destroyed, I would say there was probably a fair amount of current going through this. But again, would it really tell us anything? I would say as a minimum it would give me some level of concern that, yeah, there's probably a lot of current going through this thing, and, you know, that could be going through a human. Probably not a good thing, right? So as long as we're talking about this meter, another thing I thought I'd mention is I had the oscilloscope out. I was probing around this thing, and basically it looks like they have a sine wave oscillator built into the meter, and this runs at roughly 2.4 kilohertz. So this sine wave here has some known amplitude, and I believe that they are coupling that then through the ground lead. So let me just show you something here. If I put this thing into our non-contact mode, and all I'm going to do is take this wire, our return path, and I'm going to slide that into the jaw. See how the ground indicator goes off? So that's closing that circuit, right? So I think the way this works is they're demodulating this 2.4 kilohertz through that capacitive plate. So again, you have a wire that's sitting in the middle of the jaw, and this is forming a capacitor down to our sensor plate here. And so now we're injecting a sine wave essentially onto this wire, you know, and that could be through this ground path here, you know, through the negative lead up through our path here. If I put a piece of wire in here and I measure the capacitance up to the plates, this is quite small. We're talking about, you know, 20 to 40 picofarads kind of range. So at the 2.4 kilohertz, we're talking about, you know, X sub C's in the, you know, 10 mega ohms or so. And I think it's when they decode this 2.4 kilohertz, I'm putting frequencies in there that are, you know, superimposed. They're kind of in that frequency range, and it messes up with their algorithm that's trying to decode this thing in the first place. You know, I mean, it would make sense to me that the meter would have troubles with higher frequency, you know, being superimposed on top of this return path. Typically, when you're looking at power, I think they measure 40 harmonics out or something. That's 40 harmonics off of the 60 hertz. You know, so you're well above this 2.4 kilohertz. So again, just by design, I'm kind of surprised that the meter has trouble with that low a frequency. So here's my little human simulator. So basically all I have here are 3 old LEDs, and they're in series with a 1K ohm resistor. And then I have a piece of copper braid soldered to the end of this. And we're going to use that to attach to this button with a piece of tape. That should make fairly good contact. And this is going to be our negative side. And I'm going to inject on the positive side here. So let's go ahead and inject 5 pulses. And let's see if we detect anything on our LEDs at all. So again, this is 1000 volts off the transient generator. It has a 2 ohm source impedance. So you can see that was not enough to cause the meter to break down. So let's go ahead and increase this. Now again, I'm leaving the meter in the volts AC-DC mode. If you remember on that last schematic I drew, this junction right here feeds to the selector switch. And then this went down to a series of transistors that act as the high-speed clamp. So this is our current source when we were trying to measure resistance. So what I'm doing by having the switch in this position, I'm not engaging these transistors which are located down here. And the reason I'm doing that is I know that we can damage those parts. Obviously we've done it before. So hopefully, keeping the switch in this mode, we won't damage that. But again, it still keeps the rest of that circuitry engaged. So now what we're going to do is apply a 3000 volt, 100 microsecond full width half height with a 2 ohm source, again across the meter. And let's see if we can detect any kind of light coming off of our LEDs. Just barely. Alright, let me turn off the lights. And let's see if we can see them now. It's just barely. Let's go ahead and increase this. Okay, so I've reprogrammed the generator for a 5000 volt peak. Again, this is a 100 microsecond full width half height with a 2 ohm source impedance. Again, I'll go ahead and turn off the lights. Again, this is more than enough to break down the meter. It's definitely quite a bit brighter. So the fact that we're able to light those up at all, and we have a fair amount of current flowing through those. Alright, so here you see I have my Brahmin. It's attached in series with a power supply going up to our LEDs. So right now the LEDs are totally off. What I'm going to do is just turn up the current a little bit until we can get some sort of brightness. And so currently you can see we're putting roughly 12 microamps through this network. We go ahead and turn off the lights again. And you can see they're quite a bit brighter. It's not a good indication of how much current we're pushing through this meter though. What we do know is it's not enough energy to actually damage the LEDs. Alright, so you can see I've placed my meter inside of our little box here. I'm not worried about the meter coming apart, but I am certainly worried about these LEDs possibly coming apart. So I just want to deflect the shrapnel if they do explode. Here you can see I have our medium energy transient generator attached. I call this my half cycle line simulator, and that's because this roughly puts out what I would consider the amount of energy off of a half of a AC line cycle. Again, this would still be nowhere near what the IEC standard would call for a surge test. But if you've watched my videos, you've seen the damage that this combination of generators can cause. Again, this supplying the very high voltage peak that hopefully breaks down the device that we're testing. And again, this transient generator is supplying the energy to fuel that arc once it ignites. Again, this test isn't going to be very conclusive. Obviously, if the LEDs come flying apart, we have a little bit of energy coming through them. You know, maybe there's some concern there. If they don't, and they're still fine after this test, you know, obviously there's not a whole lot of energy there, I guess. But again, how much does it actually take to injure or kill a human? I really have no idea. So again, I don't really know how we quantify this test other than saying, you know, the LEDs lived or the LEDs failed. And I can tell you roughly how much energy is available to them, you know, if something goes wrong and the meter breaks down. But that's basically all I can tell you. So let's go ahead and we'll give it a try. Again, this will just be a single transient. And that's it. This generator, you have to be a little careful with this because, you know, there is enough energy here that it's lethal. So again, we have our jumper stick out here. We'll go ahead and short this thing out. Alright, as you can tell, it definitely didn't crack the LEDs. You saw them light up, but really that's about it. The meter still seems to be fine. Let's just go ahead and hook up our LEDs to our power supply. And you can see they still light up just fine. So no damage to our LEDs. So yeah, I'm going to say not a whole lot of energy was really present. It's definitely limited by our circuitry here, as well as the PTC and the 1K ohm resistor. Again, the PTC isn't going to open up, and it has way too much thermal mass to even react to a transient like this. Well, I think that's going to be it for this video. Again, I'm not sure really what we learned from it, but hope you enjoyed the video. Till the next one. Later.